So previous Jensen's inequality estimate the probability that x is 0. So none of the bad events happen. But sometimes we might want to also prove that this x is, say, smaller than half of the expectation. So, instead of, completely, say, in the previous example where we want to find the probability that a given random graph is triangle free, we might want to also, estimate the probability that it has small number of triangle instead of triangle free. For those situations, the previous Jensen's inequality is not good. So we can ask that is there any way still we can estimate such probability? So the following theorem actually provides such a tool. So we assume as before, delta mu m b sub I or x all assumed in the same way. And we consider some t between 0 and mu. Then what we have is the probability that x is smaller than mu minus t is m mod e to the negative t squared over 2 mu plus delta. So if we have this, then, for example, if we want to find the probability that number of triangle is small, then let's say x is the number of triangles in random graph, then we can actually show that the probability that it's smaller than its expectation by some constant smaller than 1 is actually, if you compute this, so we know that mu is roughly some constant times n to the 3, p to the 3. So you take this t as c times mu, then this is c squared times mu squared, which is this. And again, mu is n cube p cube times some constant. And delta is, again, you choose 5 vertices. And then 2 triangles sharing one edge. So p to the 5, m5, p to the m4. 4 vertices and 5 edges, p to the 5. And let's say some constant depending on c. Large c, small c. So this is capital C, this is small c. Then this theorem gives this. Again, using this, we get this probability. But if you think about this holds when x equals 0 as well. So if you go back to the previous this theorem that we proved, we know the probability that the x is 0. So that provides a lower bound of the probability that x is smaller than 1 minus c times mu. That lower bound is more or less same with this upper bound, except this constant vector is maybe different. So this is, again, as best as we can do, up to a multiplicative constant on the exponent. So now let's prove this. So again, somewhat similarly to the extended Jensen's inequality, we will use probabilistic method to prove a probabilistic theorem. So let Q be a number which we determine later. And for each alpha in this index set I, let J sub alpha be independent random variable which is 1 with probability Q and 0 with otherwise. Yeah. Maybe I don't need to write it this formally, but let's say n and T be the random subset which is collection of alpha where this J alpha is 1. So you collect all the indices which has 1 here in this J alpha. In other words, for each index you with probability Q you add it to T, and with probability 1 minus Q you don't add. And we write, say, and for S, which is a subset of this I, let's write X sub S be the summation of all alpha where the, let's say, indicator random variable be alpha. So which means that among S, so there are indices, and we don't consider all indices, but among the indices inside of S, we count the number of bad events that happen. And T is this random set, so we can consider X sub T. So there are two randomness. One is you choose these indexes as random, so we have indices. And then for each indices, we check whether this bad event happens or not. This bad event happens depending on random set R in the previous setup. And we count the bad set. So there are two layers of randomness. Then what we have is, if we fix one randomness, so if we fix a choice of these two randomness, we fix one choice here and this is still random, then we can estimate the probability that once we know X, meaning that we know which event alpha 1, alpha B1, B2 to be, this event, let's say B alpha is in I, we did this experiment and then we know which one happened and which one doesn't happen. Assuming that the number of bad events in T is 0, is this 1 minus Q to the X. So in other words, if this is K, then we know that those K events are not included in T. That's exactly this event. So in other words, if we know, let's write this in this way. So if we fix this value as certain number, then this is 1 minus Q to the K. That we know. So what happens if we take an expectation of this 1 minus Q to the X? This is nothing but the summation of probability that X equal K. You take the 1 minus Q to the K, and where K is all possible value, 0 to, say, maximum number, we can get this. But if you consider this, what's this expression? because of this expression is nothing but the probability that xt is 0, assuming x is k. So conditional probability, I mean, we know that this conditional probability times this is nothing but this. But we are adding up all possible values of this. So this entire expression we has, I mean, this part does not do anything. So this is just the probability that xt is 0 in this 2-layer of random event, right? But we can again write this in a different way. So for each s, which is subset of I, we consider the probability that t is exactly s, and probability that xs is 0 for specific set s. But this we can actually measure it using Jensen's inequality. How? We let mu s be the expectation of xs and delta s be the all alpha and beta in this set S, the joint probability. Then Jensen's inequality says that it is at most e times e to the negative mu s plus delta s over 2. Right? And what's this probability? If you add up for all s, that adds up to 1. So this is, we have certain number e to the, say, alpha I, say gamma I, and delta I, summation I is 1 to, say, some number t. But what we know is that if you consider exponential function, then that's convex. So if you take these two and take the weighted average, it's always above the graph. That means by the convexity, this is at most, because this sums up to 1, this is at most e to the weighted average. So you apply that, then this is at most exponential times summation of probability t equals s times minus mu s plus delta s over 2. But if you consider mu s probability t equals s, this is nothing but the probability, I mean expectation of xt, because this is probability that t equals s times expectation of xs. So you choose t first. You fix t, and once you fix t, now you roll the dice and then, I mean, choose this random set R, which decides which of the bad events happen. and that's in here. So 2 layers of randomness. So this is just same as this. And this is, I mean, you say roll the dice first. So you swap the order. You decide R first and then T later. Then what happened? This is nothing but you use the linearity of expectation. The indicator variable for alpha, B alpha. And each of these probability that the alpha is in T, which happens with probability Q. So this, let's say this is mu prime, that mu prime is Q times mu. So this part is mu and Q. And similarly, if you have the, again, probability that T equal S and probability B alpha and B beta, where alpha and beta is in S. So again, you swap the order of randomness. So here you choose T first, and then you reveal each of the bad event happen. But you swap the order, you reveal which of the bad event happen first, and then choose which are included in T. Then, let's say this delta prime is Q square delta. Because once bad event, this happen, and alpha, it only contribute if both of them belong to T, which happens with Q square probability. So, using this, we know that this is at most e to the negative mu prime plus delta prime over 2, where mu prime is mu q, delta prime is delta q square. So we have this. Now what we do is we use Markov. Markov's inequality implies that the probability of x being smaller than mu minus t is same as the probability that 1 minus q to the x is at least 1 minus q to the mu minus t. Because 1 minus q is smaller than 1, we have a flipped direction of inequality. So what's this? So by Markov's inequality, this is at most the expectation of 1 minus q to the x. You divide by 1 minus q to the mu minus t. But we know this expectation is at most this. So this is 1 minus q to the, say, minus mu plus t e to the minus q nu plus q square delta over 2. So we have this. So now we need to decide q. So let q be so that one minus q is same as e to the negative lambda, where lambda is 1 over mu plus delta. That's our choice. Then we know that e to the minus x is roughly 1 minus x plus x squared over 2 plus some, cube term. So from that, what we know is q is between lambda and lambda minus lambda squared over 2. Then, now, probability that x is smaller than mu minus t is exponential of here, what we have? 1 minus q is e to the negative lambda. So if you apply that, this is lambda mu minus t. And this part, q is between these two. And we want to get the upper bound. And there is minus. So you take the smaller one, then you get the bigger number. So this is lambda minus lambda square over 2 mu plus. Here you have plus positive and yeah, positive. So you take this number, then you get upper bound. So this you plug in lambda, then lambda square delta over 2. So this is the upper bound. So you get lambda mu, and this lambda mu cancels out. So lambda t plus lambda square 2 mu plus lambda square delta over 2. So you get exponential of minus lambda t plus lambda square over 2 mu plus delta. But what was the choice of lambda? Is this. So you just plug that in. Then this is the desired bound. So this proves this inequality on the lower tail. So lower tail means that we generally want to show that some x is concentrated around its expectation with high probability. If you measure the probability, then this is small, but with high probability, it's here. So what it shows that is that the probability that it's lower than this mu of t is small, and then so this lower tail has a small probability. But what about our upper tail then? Can we also show this similar bound? Actually, no. If you, this kind of statement does not hold for upper tail. So consider again G and P, and we want to count the number of triangles. Then, what do we have here? So expected number of triangles is roughly n3, n to the cube, p to the cube. So if you show that the probability that the x is smaller than half mu is, we have it here. Which is if p is bigger than, say, 1 over square root of n, so this is bigger, so it gets, let's say p is quite big, then this probability is roughly e to the negative theta of n square p. But we want to ask that can we bound this with a similar bound? The answer is no. Because what's the probability that x is bigger than, say, 2 nu? So 2 nu is roughly, say, some number, okay, 10 times n cube p cube. Then there are several ways to get this x. One of them is that you have, say, 10 MP vertices. and every pair here are edges. Large clique of size np. Then you get the 10 np, choose 3. Many triangles, and we get this. So this is at least the probability that, and this number is bigger than this, right? Which is bigger than this 2 mu. So it has a clique on specific 2 np vertices. It's at least, I mean, you have a 10 np vertices, and there are this many pairs. Every one of them is an edge. Then roughly what this is, I mean, if you consider p is 2 to the log p, and you multiply them, then this is e to the, say, some constant times. What's this? This n square, p square, and log 1 over p. If you think about this, then n square, p square, I mean, this is p times p log 1 over p. This is much smaller than n square p, because p is still, let's say p is little of 1, of course. Then p is very small, so that if you compute this is also something going to 0 as p goes to 0. So this is much small, so this number is much bigger than this. This is small omega of e to the this number. So while on the lower tail we have a concentration, I mean probability, this small probability we can bound the probability of lower tail, but for the upper tail, similar one is impossible. We actually know that if p is not too small, then the probability that this is bigger than, say, twice of the expectation is. So here we prove just lower bound, but the more or less it's also upper bound. So this is actually kind of correct asymptotic in this triangle counting case, but this is more complicated, so we will not deal here.